Okay, guys, so I'm going to have a quick lecture today. This is an entirely recorded lecture to try to get us caught up. And this is on using SPICE. I hope this is, a simulation program that I hope most of you have some exposure to. So this is a program that is developed to do analog level simulations of circuits, and there's a bunch of versions available for the project. For our project, I've suggested we use LT-SPICE, but other versions of P-SPICE. There are there's H-SPICE, and Cadence has its own version called Spectra. So there's a bunch of different pieces of software that you do the same simulation. And this basically is a full simulation. And what you do is you create your schematic or netlist in the program, and then you give it the model file. So I put up a model file for the 180 nanometer TSMC process. And the model files could be anywhere, they go anywhere from a level 1 type model, which is kind of our simplified IV characteristics, all the way, there's level 49, there's different ways of, there's many levels of modeling that can get pretty detailed. So, but basically it's a full up simulation. It's solving differential equations at each node. And anyway, it's a real powerful program. What can I say? There's the actual writing of a SPICE stack. It could give it a net list, or most of the time we actually draw a schematic and our tools translate to a net list directly. But it's still, I think worthwhile to be able to look at the net list. A lot of times when I try to debug, I look at the net lists, and I also sometimes it's just easier to go in and modify the net list. And there's some things that it's difficult to do in the schematic. So when you're like arraying things or something like that, it might just be easier to go straight into the net list. So this is talking about how to write that SPICE net list, or it's really called the SPICE deck for whatever, going back historically to when this was, computers with card readers would run this program. But the main thing I think is to make your schematics like sensible, get a decent level of hierarchy in your schematics. And so it's easy to debug, and it always, don't jump, especially when you're starting, don't jump straight into trying to simulate your entire circuit. I usually just sort of throw in an inverter, and that's what I start with, just to see if the model files make sense. I might do an IV curve of the NMOS and PMOS. Again, just like you would with a regular computer program, sort of take it step by step rather than jump into the, all the way in, and, you might run into trouble, and you might not even know it, or it'll be hard to debug. Okay, so here's a example of a netlist. And so this is, so this would be what it would look like if you were in the schematic editor. So you just put in the resistance, capacitance, and then, or, either it's outputting this automatically, the tool, and simulating it, or you can just write the net list. So here are a few of the items here. So here's the resistor. Notice it has 2 nodes and a resistor value, and the capacitor, 2 nodes and a capacitance value. And K is 1000, F is femto, 10 to the minus 15. Okay, so F is equal to 10 to the minus 15, which is you see that a lot in on-chip simulations. By the way, one thing to note is be careful about not putting in spaces here, like 100 space F or something like that. It'll give you, the program won't quite know what to do with that, and you'll run into problems. So put the number in and the units without spacing. Okay, here's the input voltage. This is an independent voltage source. It goes from in to ground, so I guess this would be in and this would be ground. And this says it's a piecewise linear signal. And a piecewise linear basically gives each time point and the value thereof. So let's see if I can draw this, what this piecewise linear signal would look like here. So it says, let me see, so it's got 0 volts and 1 volt. So it says at time 0 picoseconds, it's 0, so that's one node, 1 point. It says at time 100 picoseconds, it's also 0 volts, okay. Then it says at time 150 picoseconds, not drawing this to, what do you call it, scale, it's 1 volt, okay. And at time 1 nanosecond, which is like going way out here, 1 nanosecond, it's 1 volt. So the waveform, basically the tool, all it does is it connects those points and that becomes your waveform. So I'll do this. So, and this. So it looks like a rising edge signal, and it's, the rise time is 50 picoseconds. So that's what this voltage statement looks like. Let's see, go back to red, okay. And then, so this is how you've set up your simulation, and then to actually run the simulation, you need a .trans statement, which says do a transient analysis. You can force the steps size to 20, whatever you like here. This is in 20 picoseconds. But the tool, that's setting the maximum step size. That's telling the tool don't take too many big steps. But the tool, if it decides it needs shorter steps, like it needs to go to 1 picosecond, because there's some, I don't know if you had some inductor or something, there was some high frequency events here, it would just automatically by itself go to lower frequency points. And then this 1 nanosecond tells it to stop the simulations at 1 nanosecond. This dot plot statement tells it to do a graphical plot of the in and the out, assuming these are the node names. And then you always need a dot end statement, okay? That's always required. Anything with a star is a comment. So the tool won't see that. And also the tool does not notice the first line of a file. I think it just ignores it. Okay, so basically you'd end up with something like this. Note this is our input waveform that the piecewise linear input waveform that we looked at, and here's the output of the RC, okay? So these are the different types of sources. We already looked at the piecewise linear source. There's the DC source, which is, the DC voltage. This is 2.5 volts between VDD and ground. And then you have a pulse source. So here, there's the name of the voltage source, the 2 nodes, pulse as the pulse. And here, 0, this first point, is when this thing starts. Sorry, it's the 0 is the low voltage, 1 is the high voltage. Okay, so this would be V1, V2 in this plot. Okay, 0 picoseconds is when things start, so it's T sub D. Okay, 100 picoseconds is the rise time. the second 100 picosecond is the fall time. It's just sort of the position along this line is what decides what they are. And then this is the amount of time that the signal stays at the V2 value. So this would be it's called PW in our graph here. And then this is the period. So the whole thing repeats every 800 picoseconds in this particular case. Okay, so basically you can end up with a whole bunch of different components, all the components you need. Anyway, you have I don't know, everything here: voltage sources, different transistors, transmission lines, subcircuits, you name it. So, and then here's some talk about the units. So for capacitors, usually you're kind of, and for our simulations, usually in your femtofarad range. You might end up in the picofarad range as well. And sometimes attofarad, pretty rare. But anyway, sort of usually you see femtofarads or picofarads. If you're in the nanofarads or above, like microfarads or something, you're off. Like you're off the you've lost your way, kind of on chip. You rarely see nanofarads of capacitance or microfarads, etc. Okay, for resistances, usually you're talking about kiloohms or mega ohms, that kind of thing. Sometimes you see milliohms. So these are the kind of the values. So one thing to remember here, which is is different than what we normally do, mega, which is times 10 to the 6th, we usually put a capital M, but if you put an M, SPICE doesn't distinguish between lower and uppercase. So if you put an M in, it'll think it's a milli, not a mega. For a mega, you have to use X. Okay, and again, remember, don't put spaces here. Okay, and you don't need to put this capital F for farads because it just looks at that first F and ignores the rest. Okay, here's another deck that's for DC analysis, and this is to basically get our IV curves probably. So it's gonna probably have VDS versus IDS for different VGSs. Okay, VGS1, VGS2, VGS3. Okay, so this is the circuit. It's basically put a voltage source on the drain source of the NMOS and a voltage on the gate source. And it's calling this model file. So this is the model file for this transistor that's provided from the foundry. You can set the temperature. This option post is for graphing. I don't think we'll need it. Okay, and you have two DC voltage sources, which is the drain source and the gate source, and then you have your transistor. So anything starting with an M, so M1 would be, this is a MOS transistor. Bipolar transistors start with a Q. We're not dealing with bipolars in this class, but anyway, M1 is, so M says that it's a MOS transistor, and the 1 is the number for that particular transistor. So you'd have like M1 through M, whatever. Let's say if you have 100 transistors through M100, it could be called, or it could give them any name, like M. Anything after M is like the particular name. So it could actually call it MBAR to distinguish that particular. It doesn't have to be a number, in other words. Okay. Then there's a drain, gate, source, and substrate. This tells it it's an NMOS, and this has to be the same name for the NMOS transistor in the model file. So I have to go look in the model file for what the NMOS model is and put that here, okay? And then you're giving the width and the length, okay? And then you're doing a simulation. We looked at the RC schematic. That was doing a transient simulation. Transient means changing with time. here's a DC simulation, and it's set up in a loop. So what it's doing is it's basically stepping through. What is this thing doing? No, I think this is actually doing the it's for different VDSs. I think it's doing different, sweeping the VGSs. So it's probably what it's doing is something like this. It is probably doing something like stepping through VDSs. So it goes through, VDS is 0. So it's probably, let's see, what would you do? Almost seems like you want to, this would be trying to do VGS. So basically it's got an inner loop, okay, which is VGS from 0 to 1 in 0.2 volt increments, and an outer loop, which is 0 VDS from 0 to 1 in 0.05 volt increments. So I'm trying to figure out, like, is this for, I'm not sure if it's used for IDS, I guess we'll see in the next graph, versus VGS, which will kind of like curves that would look like this, sort of, or whether it's for VDS versus current. Well, I guess it's for different VGSs for VDSs, okay? IV characteristics. So was the first thing I was thinking of. Okay, so you can do the IV characteristics using these DC models, and then you can also sort of zoom in to low gauge source values and look at the leakage currents, the off currents, okay? And then you can, this is a plot of IDS versus VGS. Okay, and you can extrapolate the threshold with something like this by looking at where this line, this is the subthreshold region. So if you want to see the threshold as it's defined in our simple models, you have to extrapolate this down to where it meets the curve, sort of from asymptotically. Okay. So anyway, every time I start designs with a new process, what I do is I, make these curves for myself just to get a feeling for, say, a minimum size NMOS and minimum size PMOS to see what these things look like, and also this, this VGS versus IDS. Okay, so let's see, what is this thing saying? I think this is showing that for, we could simulate the effects of basically different length devices. As the length goes up, I think we talked about this a little bit, the threshold voltage goes down because we have some issues down here, and also as the temperature goes up, the threshold goes down. And then, so this is typical. So this is that corner of the simulations, a different simulation, a different temperature. This is slow, meaning both your NMOS and PMOS are slow, and this is fast, both NMOS and PMOS being fast. Okay, so this is just simulating different parts of the process. So this is just saying you can simulate different process corners, okay? So this is back to the NMOS model name. So anything with M is a MOSFET, sorry. And then you can give it whatever name you want, letters or numbers. And the nodes are drain, gate, source, and body. And the type, again, has to be the same as model file name. Not the actual name of the model file, but the name of the transistor, same as name of NMOS in model file, or PMOS, whatever device you're trying to look at. And then you have the width, length, and then you have the area of the source, area of the drain, perimeter, source perimeter of the drain. Okay, which is what you have to make sure you get all the different parasitics. So let's say I'm going to draw this thing. Let me just erase this. So let's say I draw the active. Okay, so we're talking about an NMOS. And then I draw the poly. So this ends up being the, I don't know, drain or source or vice versa, whichever way you have it set up. So the area of the source or drain, the area is basically you've got to get this whole area here. Okay, so you put that in the area. And remember that, you know, if this is 1 times 10, let's say this is a micron by a micron wide. I'm just going to use that as an example. Remember that if you multiply these two together, you're going to end up with 1 times 10 to the minus 12. So make sure your area drain, area sources have sort of big negative numbers here on the exponent because you're multiplying two small numbers together. Now the perimeter of the source and the drain are just usually it's these 3 sides of the device added together. So let me just draw that orange. Okay, and that'll be in 1 times 10 to the minus 6 or something. So in this case it'd be perimeter of the drain would be 3 times 10 to the minus 6. Because there's no diffusion here, so we just have these 3 sides. Okay. So here's another transient analysis. They've parametrized the supply voltage, so there's this variable they've defined to be 1. They've defined a scaling of 25 nanoseconds, or 25 nano, sorry. So when they say L is equal to 2, okay, it's 2 times 25N. So that they've just sort of, you know, I guess it's parameter independent. So this would be like 18 times 25 nano, etc. These are 2 transistors, and looks like an NMOS and a PMOS for our inverter, pulse input, supply voltage, transient simulation, and the parametric. And notice they've used this parameter supply here. And the reason you would do that is so you can easily change this thing and the top, you know, if you want to sweep that or something. And notice they've running it at a temperature of 70 degrees Celsius. So this is in Celsius. And then they're including this model file. Okay. And notice there's always an end set up. And you get something like this, which note they've got a, let's see, they've got a, the V input pulse goes from 0 to the supply voltage, 50 picosecond delay, 0 picosecond rise time, and 0 picosecond fall time. Okay, so this causes some like nonsensical things happening when you don't have, see the simulation, you don't have a load capacitance. So what you see is this is the input. So this is a very fast rise time. And like an unrealistically fast rise time for the input. So what happens is if you have a N or a P, you actually have this drain source capacitance, say the drain of the N or the drain of the P, there's a drain gate capacitance, feedback capacitance. And when you have an incredibly fast rise time, this basically carries through to the output momentarily and gives you this really huge peak, which doesn't really happen in real life, because what happens is, one, this is being driven by another gate, so it's a slower rise time. And then also usually you're driving a gate which has some load. So in reality, this won't exist. So if you're seeing these kind of overshoots, it probably means you're having unrealistically fast input rise fall time, and or you don't have like enough loading. Okay. Another nice thing in SPICE is subcircuits. So you can define a, say here they've defined an inverter, okay, in a subcircuit statement. And the subcircuit name is inv, and then basically it has these two nodes, A and Y. And then it's got these parameters that gets passed on to the subcircuit, and then you can call this in your top circuit in different places. So like you can just drop inverters and have these parameters to decide how big they are. So here's something that we're going to use in our project, project 2, which is the simulation of the speed of a device. Okay, so this is checking for the speed of this inverter. Okay, so what it's doing is it's stepping up the size of these inverters by a factor of 4 in each step. It's going from 2 to 8, 8 to 32. These first two inverters are just there so that they're slowing down this rise time from our source to something reasonable, something realistic that goes into this device under test. And then this is basically the realistic loading for the inverter for this output capacitance. And then again, notice it's gone up by a factor of 4 in size. By the way, these X's are the subcircuit names. So they're calling this is in times 1, times 2, but the subcircuit gets called as X1, X2, if you look at the SPICE deck. So subcircuit calls are as X's, okay? The actual sizing is here and here for the P MOSFETs, okay? So you see here the subcircuit calls are X1, X2. They're actually calling the subcircuit. And this is basically some measurement parameters. So this is kind of a nice thing because you can set this up in the netlist to actually automatically measure, let's say, rise, fall times, etc., parametrically, and you can do sweeps and stuff like that. I'm not really sure what LT SPICE will allow us to do, but definitely if you go play with the netlist, you can do this by hand. And these are the different nodes in the simulation, A, B, C. So basically C and D, this is the nodes we're interested in, or devices between C and D. Okay, let me see if I can find C. So here's C. No, sorry, I think this is C. I think this is C. And where is D? D is this guy here. And notice here's the input from the voltage source. So it's like a very sharp rise time. A is that first inverter, and B is, so I'm sorry, the A is the output of the voltage source, B is the, I guess the input to the second inverter, B is the input to the second inverter, and C is the output of that second inverter. So by the time you've created C, A and B, or those first two inverters, are just kind of creating this realistic rise time for C. And then the delay of E and F are just for loading D. So the actual rise, this is the 50% to 50% delay for that inverter that was sandwiched in the middle that we were interested in, this guy. Okay, and this is the prop delay for the rise, prop delay for the fall, 50% to 50%. Okay, again, we'll be doing this in project 1, I think. Optimization, I won't go into. You can optimize circuits. I haven't really used this much. It's kind of a cool idea, but I don't think we'll be using it. So in the class, but we might. So here's some of the stuff you'll need for the project. So some of the things you can do is basically you can try to extract some of the parameters for the logical effort, okay, from doing the SPICE simulation. So you just do this once and get these numbers, and then you can use them for hand calculations later. So let's say the first thing you want to do is, if you remember, we were doing, we needed an R equivalent, and then we had a gate capacitance, and then we had a drain capacitance for each device. So this was our model for the N, and corresponding model for the P was the same. It had an R equivalent for the P, and R equivalent for the N. Okay, so let's say we want to figure out the C gate capacitance from our simulation. Okay, what we can do again is, this is all shaping the input. So shaping input into something reasonable. And this is loading the output. Okay, and so what you can do is you can create this guy, this C, is, again, remember, these are just sub-circuit names. So the size for this inverter and this inverter is exactly the same, and they're being driven by the same input. Okay, the difference being that this inverter on top is driving a sort of a perfect capacitor, and this inverter is driving this device, which is like the C sub G, is driving the C sub G of this very large inverter. 32 by 64, so this is a 32x, this is 64x, okay? That's what this guy's driving. So if you sweep the delay value up and down until the rise fall time of the node G ends up being exactly the rise fall time of node D, then what you've done is you've tweaked this delay to be exactly the input delay or the input capacitance of this inverter, And because the C sub G for N and P are the same, C sub G N is equal to C sub G P, you can figure out from this, you can figure out the capacitance per unit width of this process, okay? Because you're equalizing this to this, and you can basically get the value of C sub G N GP using this simulation. And this is in your in the project 1, kind of, I think it's one of the first steps you do to get C sub G for the process. Okay, And one thing to note here is for for doing this correctly, you'll need for these devices, you'd need to make the area of the drain, perimeter of drain, make all these guys 0. Area source, perimeter of source. Otherwise, because you want to kind of zero out the capacitance, this output capacitance of the inverter itself, and you just want to be looking at the gate capacitance. Okay, so make sure in this simulation you zero out these area drain, these area factors for these transistors here and here. Okay. Anyway, this is a representative SPICE stack, and here I think you can see, so where they've, in the sub-circuit for those inverters, here they've made these drain source capacitance is 0 because this simulation is just trying to get to the gate capacitance value. Okay, so you can do the same thing to get the drain capacitance of the N and the P. In this case, you have to do it twice because the drain capacitance of the N is not necessarily equal to the drain capacitance of the P. So again, here you've set up your input, and you've got 2 identical devices that you're driving with that input. And here you've set up a NMOS device. You've hooked up the gate to 0, the source is at 0, so this guy is off. And all this guy sees looking at here is the drain capacitance for the area, the drain area, perimeter of the drain. So again, if you have this ideal capacitance in the second branch and you vary this until E exactly overlaps with D, this C delay tells you this capacitance sitting on the node here. And then if you can do the same thing for a P, except instead of this, you hook up your P to look like this. You hook it up like that to your inverter. So then you just have the drain of the P set up. Okay, power measurements. You can do power measurements. I'm not going to get into that. It's a useful thing, but we won't be doing it for the project. So far we've gotten our we got our C sub G from this simulation. This is all to plug these things into our sort of hand delay model. And then we have our C sub D's here for the N and C sub D for the P. Okay, so now we need R sub N and R sub P for the resistance of the unit devices. Okay, so the way we can do that is set it up like this. We can have a minimum size device driving a fan out or variable fan out device. Okay, so let's say if you want to find the resistance of the N, the equation for the propagation delay falling is this Rn, which is we're trying to solve, times 3 times the fan out number H times the capacitance, input capacitance of the gate, plus 3 times the drain capacitance. Okay, so if you run 2 simulations, let's say you run one with H of 3 and one with H of 4. Okay, so, and look at the difference in the propagation delay fall. Okay, you'll see that, so Rn, so first for the case with 4 fan out, 3 times 4 times C plus 3 times CD minus, notice this is a delta, so you have to run once, get the propagation delay falling for the fan out of 4, and then the second time you run it again, you get the propagation delay for fan out of 3, and we multiply this by C plus 3CD. Okay, the reason this guy doesn't change is because this is the node here. We're not changing that, we're just changing the fan out, the number of inverters you're driving. Okay, so if we get the delta between those two, we just end up with 3RNC, okay? And this is C sub G. So we already have the C sub G from a previous simulation. So basically we're measuring delta T, P, the propagation delay fall. Okay, we're measuring that in our sim. We have this from the previous sim, so we can get this Rn. And then we can get the R sub P of the process with exactly the same process. Okay, so you'll be doing that as in your project. Okay, and then you can also do logical effort. Let's say you were assigned with a 2-input NAND gate, right? So basically what you can do is to set that up in a sim. This is again shaping the input, the load, etc. But basically you can scale this H, okay, numbers. So with these different simulations, so let's say 1, 2, 3, 4. So you have to run, like 4 sims, and for each one vary this multiplication factor. Okay, you'll see this in my sort of the LT-SPICE tutorial video, how you do that. And then you can measure this delay, and then you can, see how this curve changes. Okay, so you can get that curve we have of H versus delay for, for different devices. So for an inverter or a NAND 2, etc. Okay. Let's see, what else do I want to say? I think the rest of this stuff is, logical effort, simulation data for different processes. So anyway, I think that was my intro to SPICE. Hopefully, this will, between this and the tutorial on how to use LT-SPICE, you'll be able to take a good crack at the project too. Okay, talk to you guys tomorrow. Take care. Bye.